Welcome back everyone to another episode of the Reading Club, and in today's episode we will continue covering Presolve Reductions in mixed integer programming. So again, this was the paper that was written by Gurobi developers, and they describe the different types of Presolve reductions that are implemented in Gurobi. And in today's episode we will continue focusing on Presolve reduction that look at entire problem at a time, and we will look at two different Presolve reductions. So let's get started. Okay, so the first pre-solved rule that we are going to see today is called exploiting complementary slackness. Complementary slackness. Right, so if you have done linear programming before, then you might be familiar with this term, complementary slackness. If not, then let me just uh, revise it for you, just in case. Okay, so we have our mixed integer program. Let's consider its linear relaxation in this format, right? So this is the linear program that we have, and x is greater or equal to 0, and for that we have our corresponding dual, which goes something like this. So we have one variable y for every constraint and one constraint for every variable that we have. So here it will be maximizing b transpose y such that a transpose y is less than or equal to c and y is also greater or equal to 0. Okay, so this is the complementary slackness. It says basically that if so if the variable y for a corresponding constraint takes the value greater than 0 in my optimal solution, then in that corresponding solution, uh, this this inequality will be satisfied at equality, right? So basically what I'm trying to say is that if yi star, right, if this is greater than 0, then this implies that ai x star, which is the optimal solution for primal, is equal to bi. Okay, and the other way around also goes that way, right? So it is like if for a column j, if xj star in my primal solution is greater than 0, then the corresponding dual solution in the linear program, okay, it will have its corresponding. So here we have a variable, and for every variable we have a constraint over here, right? So the constraint will be satisfied at equality. So a transpose y, so this is aj y star, that is equal to cj. Okay, so that's called the complementary slackness. So the duals only exist for linear programs. There is no dual for an integer program or mixed integer program, right? So how do we utilize this complementary slackness for our mixed integer program, right? So we have mixed integer program. That means like for some variables, they are integer over here, and that this part is not really captured in the dual, right? So that's something that we have to think about it. Okay, so the way we use this complementary slackness is, first of all, uh, we will not really consider these integer variables at all, right? So we can write, if we let's say fix all the integer variables, right, to some values, let's say random values, some feasible values, then what we have left with is remaining continuous variables, and that becomes a linear program, right? So if you have already fixed all the integer variables, then whatever is left here is all continuous variable, and this entire program becomes a linear program. And for that we have a valid dual, which basically means that if I fixed all the integer programs, then some of this constraint might not be there, right? So the constraints that correspond to integer variables will be removed from this dual linear program, and remaining constraints will be there. So that's what we are going to do, right? So what we will do is we are not exactly going to fix them, but we are going to ignore them. Okay, so we will write a dual LP like this, but we will only consider the constraints which correspond to continuous variables. Okay, so these are all constraints which correspond to continuous variables in primal. Okay, so that's how we will do our write our dual program. And what we will do is that we will do some regular bound strengthening and coefficient strengthening. We can only do bound strengthening. There is no coefficient strengthening in linear program. So we'll do bound strengthening on this, and based on the bounds that based on the tighter bounds that we find, we will make some deductions by using these two conditions. Okay, so what happens is that, like, so I what I'll do again, I'll just repeat again. So it is like we have our proper mixed integer program. Okay, and we will write a dual program, but we will only consider the constraints which correspond to continuous variables in primal. Okay, so now this is a dual linear program. Then we will do bound strengthening on this dual linear program, and let's say if we find that for some y variable the lower bound is not 0 but it is strictly greater than 0, then it means something, right? So we can do this thing here, right? So what does this say is that in my primal solution we will have ai x star is equals to bi, right? So this constraint will be satisfied at equality. So if we have that constraint as an inequality, we can convert it into an equality constraint, because we have proved that the yi star, the corresponding variable in the dual, is strictly greater than 0. Okay, so and based on the complementary slackness, it has to satisfy at equality, right? And this holds true even in the presence of integer variables, because once we fixed all the integer variables, right? So this consider that inequality, and if we fix all those integer variables and move it to the right hand side, it will still be an inequality with only the continuous variables. So the entire MIP will become an LP, and it is exactly the same LP as we started with, because we completely ignored the integer variables, right, when we were looking at the dual. Okay, similarly, if we find something like this happening in our dual, right, let's say not exactly this, let's say here, let's say this part is strictly less than Cj, let's say, right? So this is strictly less than Cj, A J transpose y star. This is strictly less than Cj. If we find this part for some constraint, right? So we can find an supremum of this part, and we can prove that it is strictly less than Cj, which means that this constraint is obviously going to satisfy all the time. And in fact, it's a strict inequality, not less than equal to. In that case, we can conclude that this xj star variable cannot be greater than 0, right? So that means that it is we can basically fix it to 0, and if we have a different lower bound, then we can fix it to its different whatever its lower bound was, right? So that's the idea of using complementary slackness in mixed integer program, right? So and this is like very surprising, because technically for MIPS there are no duals, right? And we are still making use of the concept of duality from linear programming in making deductions in our mixed integer program. So that's kind of a very nice thing. And so what is the impact? It's not really a very large impact per se, right? So it's only like about 3% speed up in overall, and like and in the affected models it is like 6% speed up in where this Presolve rule basically made a change. So about like half of the models were actually affected by this Presolve rule. So the Presolve rule made some deductions using this complementary slackness, but otherwise there is still like 3% increment in terms of overall speed up. Okay, so this is kind of very nice to observe. So the next Presolve rule that we are going to look at is called implied integer detection. Okay, so first of all, not all variables are marked as integers. So there are in our MIP there are some integer variables, and there are some continuous variables. So we are focusing on this ones. Some of these variables are marked as continuous, but they are actually integer variables, right? So that's something that we want to detect. So why do we want to detect this? First of all, like technically, like having integer variable makes things harder, but the kind of solvers that we have, right? So we, if some variables are marked as integers, or like implied integers, right? So that basically means that in a primal solution, we will have these variables will only take integer values even though they are marked as continuous, or we have at least one integer value for every optimal assignment of variables for this variable. So like, let's say we have an x equal to, let's say, 5.5, then there is also an equivalent optimal solution in which this x value will be equal to, let's say, some integer value, let's say 6 or maybe something else, right? So that's another kind of way of calling something as an implied integer variable. Okay, so this is what we are actually interested in looking at. So they have implications in terms of the way we branch, right? So we can, if there are some variables which are marked as integer, then we can actually branch on them, right? So once we branch on them, we can sometimes uh, explore our we can actually we basically have more choice for branching, right? So we can sometimes we can make deductions that were not possible by only branching on these variables, right? So if there are variables over here also on which we can branch, and it can sometimes result in a smaller tree, then that's a good thing to have, right? Then also we have something called we can make some probing type of deductions on entire problem, right? We can also have better cuts, right? And coefficient strengthening. So coefficient strengthening again like requires we can only strengthen the coefficients for integer variables, not for continuous variables, right? And a lot of cutting planes we can only do it if we have all the variables are integer, or most of the variables need to be integer for certain types of cutting plane algorithms, right? So it is kind of desirable to sometimes have more integer variables than to have mark them as continuous variables. So when exactly can we mark a variable which is continuous, but we can mark them as integer? So let's take a look at this type of constraints, right? So typically, let's say if we have AIS XS, so S is here a set plus a single variable AIJ XJ, that is equal to, let's say, CI, or let's continue or using our term, which is, let's say, BI. Okay, so in this type of a constraint, which is an equality constraint, okay, so here we can mark this variable, let's say if this is the only continuous variable, right? Continuous variable in our entire equation. So all of these variables are either integer or implied integer, right? So that's one condition. All of these variables need to be either integer or implied integer variables. Second is that when we divide all those coefficients by this Aij, right? So Bi by Aij and all this AIS by Aij, all of this should be integer. If this happens, then it is kind of trivial, right? So if everything around this variable is integer, that means this is also an implied integer variable, right? So that is kind of a very easy thing to detect. So again, like this has to be an equality for that, right? And everything else has to be integer, right? So all of these coefficients, when we make this coefficient as 1, right? So when we divide this constraint by this coefficient, and all of these variables have to be integer in order for us to call this one as implied integer. And this method is called primal way of detecting implied integer variables. Okay, so next we are going to look at the dual detection method. Okay, so it basically goes something like this. So in previous method, primal method, we had our variable which appeared in at least one equality constraints. But in over here we have a variable that only appears in inequality constraints, let's say. Okay, there is no equality constraint which has this variable, and this is obviously marked as continuous variable. Okay, so when can we say that this is also an implied integer variable? So previously, when we called a variable as implied integer in the primal detection method, it was equality constraint. So if this variable would take any value that is not an integer, then it will basically be an infeasible assignment for the MIP. But here it is not the case. So this variable actually can take fractional values, but we are arguing that there exists at least one, or there is at least one optimal solution in which xj uh, is an integer value. Xj takes an integer value in the optimal solution, right? So that's something that we are trying to argue. So let's see how that argument goes, right? So the argument goes something like this, that in our mixed integer program, right? So let's say we have our optimal solution x star, right? And let's say we extract all the integer variables, and let's say we keep them fixed, okay, to those values. But the continuous variables, we keep them, like open for taking other values. Then the optimal phase, right? So the assignments of this continuous variables for which we get the same objective value, it's a polyhedron, okay, some polyhedron, right? Not in 2 dimension, but some polyhedron, which basically means that whatever the current assignment is, let's say this is the x star. It is possible to move it to its one of the vertex, okay, and we still keep the same objective value, right? So it is possible that we can move all of to one of these vertex. This is the optimal phase, okay. So all of those, every point in this optimal phase has basically the same objective value. So we can basically move it to one of this vertex. So vertex basically means two things. Either one of this constraint is satisfied at an equality, or this variable is at one of its bound, right? So that one of those two things has to happen at all the vertex. If not, then if none of those two things happens, then it's not a vertex, it's some interior point, okay. So let's take a look at both the things, right? So let's try to address both those things. So first is that when this variable is at its bound, let's say it's lower or upper bound. So let's make sure that if the lower and upper bound of this variable are integer, then we are kind of done, right? So this is my first condition, that lower and upper bound of the variable, which is what we are expecting, has to be integer. And the second condition is that all of these inequalities, when we treat them as equalities, right, the primal method is successful. Primal detection method is successful. Primal detection implies implied integer, right? So what was the primal detection method? It was basically like we make sure that all the other variables are either integer or implied integer, and all the other coefficients are integer, and basically everything around it is integer, so that this variable will only take integer value, right? So and this has to happen for all of this constraint, right? So for all of them, not just one of them. Let's for all constraints in which xj appears, right? So when we treat them as equality, right? So if any one of this constraint is satisfied at equality, then based on the primal detection method, it was implied integers. That means to satisfy that constraint, this variable has to take an integer value. That means it is taking an integer value. So by that logic, it is overall taking an integer value, right? So we have to check two things. One is that it only appears in this inequality constraints, right? So if it appears in at least one equality constraint, then we just go back to the primal detection method. If it only appears in this inequality constraints, then two things. One, we check that their bounds are integer. And second thing that we check is that when each of them individually is treated as equality constraint, right? Then the primal detection method implies that this variable is implied integer. And this has to happen for all of this constraint. Okay, in that case, we can mark this one also as implied integer variable. So this was the implied integer variable. Let's see what was the impact of this, right? So the impact was very high. It actually resulted in 13% speed up in the test set that these people had. And in fact, for harder problems, which takes, let's say, 1,000 seconds or more, right? In those cases, it actually resulted in 71% improvement in speed up, right? So this is like a huge speed ups for this kind of whenever this. So this is like for entire test set, right? So this is basically just by marking some variables as integer variables, right? So why this speed up? It's because based on because they are now marked as implied integers, we could branch on them, we could create better coefficients for them, we could create better cuts for them, and all of that kind of pays a little bit. So that's implied integer detection. Okay, to summarize what all things we saw today. So first we saw using complementary slackness. Right, so this was linear programming concept. We used this theory in our mixed integer programs as well to make some reductions. And second, we looked at implied integer. Implied integer detection, right? So those two things we looked at today. So again, this one had a very big impact because when we mark certain variables as integers, it it actually helps with a lot of other components in the search process as well, right? So it is not really changing anything. It is not really changing any coefficients or bounds or anything at all. It is not even removing the variables or constraint or anything. It is just marking some continuous variables as integers, right? So that also had a big impact. So I hope you like this video, and I'll see you in the next videos for the Presolve reductions. So bye.